So we continue with electromagnetism, and we are on the third part of the chapter, that is on electromagnetic induction and its applications to AC generators and transformers. So we are going to have this particular part in which okay, let's see. So first we have is the electromagnetic induction. We have read about that when an electric current is passed through a conductor, a magnetic field is produced around the conductor. Faraday thought, since the magnetic field is produced by electric current, it should be possible to produce electric current by the magnetic field. See, he said that if electric current can give you magnetic field, why not magnetic field give you electric current? Okay. We know that energy can be transformed from one form to another form. So अगर समझो magnetic form electric से magnetic form में हो सकता है, तो why not magnetic to electric? That is what Faraday thought about, and he came up with these proposals. So Faraday thought that since a magnetic field is produced by electric current, it should be possible to produce an electric current by the magnetic field. He performed a number of experiments and observed that whenever there is a change in the number of magnetic field lines linked with the conductor, an electromotive force, that is EMF, okay, that is a potential difference, is developed between the ends of the conductor, which lasts as long as there is a change in the number of magnetic field lines. As long as there is a change in the number of magnetic field lines. The phenomena is called as electromagnetic induction. So he said that whenever there is a change in the number of field lines being cut by a conductor, okay, so he said that whenever there is a change in the number of magnetic field lines linked with a conductor, okay, so cut by a conductor, an electromotive force. So if I have got a conductor and there is a magnetic field, ये magnetic field के आसपास में अगर है, तो ये conductor is going to be cutting the magnetic field, or we can say this conductor will be linked with the magnetic field over here. And if this linking which is there, if it keeps on changing, okay, if this number of field lines which is cut by this conductor keeps on changing, then the ends of this conductor will produce a EMF, that is a potential difference will be produced between the ends of the conductor. That means a current can flow through this particular conductor. So that's what we read out again. Whenever there is a change in the number of magnetic field linked with the conductor, an electromotive force is developed between the ends of the conductor, which lasts as long as there is a change in the number of magnetic field lines. Till that there is a change in the number of magnetic field. पहले 10, फिर 5, ये 6, फिर 2, ऐसे करके change होते रहेगा. The number of field lines which are being cut by this particular conductor keeps on changing continuously. There will be an EMF generated. The phenomena is called electromagnetic induction. Note the number of magnetic field lines linked with the conductor is called the magnetic flux linked with it. So magnetic field lines linked with the conductor, or we can say the number of field lines cut by the conductor, is also called as magnetic flux linked with the coil. So wherever in the chapter you come across the words that magnetic flux linked with the coil, that means it is the number of magnetic field lines linked with the conductor. To demonstrate the phenomena of electromagnetic induction, experiment was done. So first is, wind an insulating copper wire in a form of a spiral on a paper or a wooden cylinder so as to form a coil in the form of a solenoid. Connect a center 0 galvanometer G between the two ends of the solenoid. Then place the NS magnet at some distance along the axis of the solenoid as shown in figure 10.6. So what you are doing, it's a simple experiment. You are having a coil which is wound around this particular thing. So there is a So this is a particular kind of a coil which is there, and you are connecting it to a galvanometer which has got its center 0. So It is center zero means it is going to tell you if it is going to give a current this direction, it deflects this way. If current in this direction, it will deflect this way. Okay. And over here is one magnet which is over here like this at a distance. At a distance, you are taking a bar magnet. So we are taking a bar magnet which is stationary at this time, which is NS like this. So you can see that this is your A point, this is your B point, and this is the connection. So you are having it like this. So this is the conductor, this is the, and this is the magnet. Suppose I just take this as a magnet. What we are doing is we are going to bring this closer and going it back, closer, taking it back, closer, taking it back. यानी इसको हम लोग move करेंगे या तो इसको भी move कर सकते हैं. It's not a problem. They are basically mutually related to each other. So there should be a continuous kind of a motion of either the magnet or this conductor. So you can see that this will be having the magnetic field lines like this. So when it comes over here, there is the magnetic flux linked with the coil over here. So this coil is going to have the magnetic field lines cut by it. So that is the magnetic flux linked with the coil. So when you bring this closer like this, you will find that this is going to deflect like this. Okay, it is going to show a current flowing like this. So now here what will happen is when you bring this, if it is a north pole over here, you will find that there will be a generation of a north pole over here. Okay, so the deflection will be in this direction. This is the first condition. Second condition, I am going to bring that thing backwards. When you bring it backwards, this north pole becomes south pole and this deflection will become like this. Okay, there will be a change in the direction of the current. Initially the direction of the current was this way, by moving it in the opposite direction, the direction of current will be in this way. Okay, so first condition is when the north pole is brought near over here, this coil will be generating a north pole over here and a south pole here, and due to that the deflection will be towards the north. Now always you remember it that the deflection of the galvanometer will be towards the north of the coil. Okay, the deflection of the galvanometer will be towards the north of the coil. अगर मुझे जानना है कि क्या होने वाला है, so suppose if I take over here, this is south and this is north, then when you bring it over here, the first thing as I bring it near, it will produce a south here, and accordingly this particular deflection will be in this form. Will be this way towards the north. Got it? And if the same thing when it is going away from here, so this is going to turn into north pole and this will turn like this. Because when it goes here, this becomes north, so the direction of the galvanometer will be pointing towards the north. Okay, the direction of the current will be always from south to north or north. So direction of the current will be always such that it is moving in the direction from south to north in the coil. So observation, when the magnet is stationary, V is equals to 0, that is no velocity, there is no deflection in the galvanometer and its pointer reads 0. When the magnet with its north pole facing the solenoid is moved towards it, the galvanometer shows the deflectant towards the right, showing the current flows in the solenoid in the direction B to A as shown. So it is going to turn from B to A away. So this is the connection. It is going B to C when it is going to go in the opposite direction. Sorry, when it is going to come from here to here, so we'll see the connections once again as per the textbook. So this was the first initial condition. So initial condition के हिसाब से what we are reading right now is this was condition 1 wherein no current is flowing through the circuit because this is stationary, and then you are bringing the first, this is north and this is south, the first thing you are bringing it closer. When you are bringing closer, there will be a north pole induced over here. Due to this is going to deflect towards this, and the flow of current will be in this direction with the south over here. Okay. As the motion of the magnet is stopped, the pointer of the galvanometer comes to zero position. This shows that the current in the solenoid flows as long as the magnet remains moving. So as soon as you bring this over here, so ये ऐसा था, इसको इधर लेके आया, फिर यहाँ पे स्टॉप करना पड़ेगा, उसके बाद मूवमेंट आएगा. तो जब भी स्टॉप करेंगे, automatically this will become like this again. The next is when you are, so this is stops over here. The next condition is when you are moving it this way. At that time, the north pole is going away, so it is going to produce a south pole here. And at that time, this is the north pole, and accordingly, the magnet, the needle, the galvanometer is going to show it this way, that the current is flowing in this direction. So if the magnet is moved away from the solenoid, the pointer of the galvanometer deflects towards left, showing that the current in solenoid flows again, but now in the direction A to B, which is opposite to shown in the figure. If the magnet is moved away rapidly, the deflection in the galvanometer increases, although the direction of the deflection remains the same. It shows that now more current flows. So if I'm bringing it faster, if I bring it slowly, तो ये deflection भी slowly जाएगा. पर अगर मैं fast करूँगा, तो ये भी फटाक से जाएगा. मैं fast ऐसे करते जाऊँगा, तो ये भी ऐसे करते जाएगा. Okay, so the deflection is directly related to the motion of the magnet. Faster the motion, more will be the current. If the magnet is brought towards the solenoid by keeping the south pole towards it, the pointer of the galvanometer deflects towards the left, showing that the current in the solenoid flows in direction A to B, which is opposite to the shown in figure in 10.29b. Exactly similar observations are made in the galvanometer if the magnet is kept stationary and the solenoid is moved. So if it is stationary and if this is moved, we get the same result. There is no change in the results whether the magnet moves or the solenoid moves. It implies that it is a relative motion between the solenoid and the magnet which produces a current. So it is the movement, the current is going to be formed because of the relative motion between the two. Okay. So, it is the relative motion between the solenoid and the magnet which produces a current irrespective of whether the magnet moves or the solenoid moves. So, whether any of them move, the main thing will be that the current is going to flow when there is a motion. It will stop when the motion stops. Conclusion from the above observation, Faraday made the following three conclusions. A current flows in the coil only when there is a relative motion between the coil and the magnet. First thing, motion is the most important thing. If motion is not there, no current flows. Second, the direction of the current is reversed if the direction of motion or polarity of the magnet is reversed. So, if the polarity of the magnet is reversed or the direction of motion is reversed, then the direction of the current is going to be reversed. And of course, as usual, you can increase. The current in the coil is increased by the rapid motion of the magnet, the use of a stronger electron. If the magnet is stronger, then also this will give you a more current. And thirdly, increasing the cross-section area of the coil, and by increasing the number of turns in the coil. If I increase the number of turns in the coil or increase the cross-section area of the coil, then also I am going to get a more amount of current flowing through. So the current in this particular coil will be dependent on three factors, or I can increase the current in by three methods. One is by increasing the speed of this thing, or by increasing the speed of this movement, that is a rapid motion. Secondly, by increasing the strength of the magnet over here, or by increasing the number of coils or the cross-section area of the coil. So that is the three ways by which you can increase the current which is going to be generated by this particular arrangement. So what is the explanation towards this thing? When there is no relative motion between the magnet and the coil, total number of magnetic field lines of the magnet passing through the coil, that is the magnetic flux linked with the coil, remains constant. Therefore, no EMF is induced in the coil and no current flows in it. So, when this was stationary, तो क्या था? जो भी मैग्नेटिक फील्ड इसको कट कर रहा था वो स्टेशनरी था, यानी ये मैग्नेटिक फील्ड अगर है भी इधर, सपोज इट्स अ वेरी स्ट्रॉन्ग मैग्नेट, सो देयर इज अ मैग्नेटिक फील्ड ओवर हियर, but the magnetic field which is cut, the number of lines which are cut by this conductor is going to remain constant, so it is not changing. When there is a relative motion between the coil and the magnetic flux linked with the coil changes. For example, in 30B, the coil is moved towards the north pole of the magnet, so the magnetic flux to the coil increases. Similarly, if the coil is moved away from the north pole of the magnet, the magnetic flux to the coil decreases. So, if I am bringing it near, तो जैसे मैं इधर पास में लेके the magnetic flux will be much more, the cut will be much more. If I bring it back, the magnetic flux will keep on decreasing. So you can see that पहले जितना पहले दूर था तो magnetic flux कम कट हो रहा है, पास में कट ज़्यादा होने लगा, और ज़्यादा. When it is going back, when it stops over here, then it is going to remain the same. The magnetic flux linked with the coil are being cut, but they are remaining same. They are not changing. That's why there is no current flowing. Because current will flow only till the time there is a change in the flux linked. Okay? Only if there is a change in the magnetic flux linked with the coil, there is going to be a current flowing it. If there is no change, there is no current. So, then when you are bringing it backwards, so अभी क्या था, पहले बहुत कट कर रहा था, धीरे कम कट करने लगेगा, and it will almost become zero. So at that time, again there is a change in the magnetic flux linked with the coil, and accordingly there will be deflection in the galvanometer. Similarly, if the coil is moved away from the north pole of the magnetic flux to the coil decreases. Due to the change in the magnetic flux linked with the coil, an EMF is induced in the coil. The induced EMF causes a current to flow in the coil if the circuit in the coil is closed. Thus, electromagnetic induction is a phenomena in which an EMF is induced in the coil if there is a change in the magnetic flux linked with the coil. So, what is electromagnetic EMF? Electromagnetic induction is that an EMF is generated in the coil when there is a change in the magnetic flux linked with the coil. In electromagnetic induction, the mechanical energy spent, that is work done in moving the coil or the magnet to change the magnetic flux, is transformed into electrical energy in the form of current in the coil. So here the mechanical energy over here is getting converted into electrical energy. Note, in figure 10.31 shows two coils P and S kept near each other. The coil P is joined to a cell, key and a rheostat, while the coil S is joined to a center zero galvanometer. If the current in the coil P is changed, the magnetic flux produced by it changes. So, the magnetic flux linked with the coil S changes and an EMF is induced in the coil S, due to which the deflection is observed in the galvanometer connected to it. The EMF is induced, or the deflection lasts so long as there is a change in the current in the coil P. So you can see that they have taken two coils. So one coil over here which is connected to a resistance and everything, and one coil over here which is connected to a galvanometer. If we are changing the resistance over here and hence changing the current passing through this, there will be an EMF which will be induced, because this will be having its own magnetic field, और ये यहाँ पे change in the current is giving rise to the change in the magnetic field, which is giving rise to the number of magnetic field line cut by this thing. See, ये पहले समझो हम लोग ने current कम रखा तो magnetic field line is only this much. उसके बाद कम ज़्यादा किया तो magnetic इतना बढ़ गया. So automatically the number of field lines cut by this one keeps on increasing with the increase in the current. If I decrease the current, again it keeps on decreasing. So by the change in the magnetic flux, or change in the current passing through over here, the magnetic field lines are changing, and accordingly there is a change, and hence the current is going to be flowing in this particular coil. The coil P in which current is varied is called as the primary coil. So this is the primary coil, and coil S is the EMF is induced. So here the EMF is induced, this is called as the secondary coil. This is the principle of the transformer as such. The direction of the induced EMF in a coil S depends on whether the current in the coil P is increasing or decreasing. This is the principle which is used in a transformer. Now let's see the Faraday's law of electromagnetic induction. On the basis of the above experimental observation, Faraday formulated the following two laws of electromagnetic induction. First, whenever there is a change in the magnetic flux linked with the coil, an EMF is induced. The EMF induced lasts so long there is a change in the magnetic flux linked with the coil. So, yeah, whenever there is a change in the magnetic flux linked with the coil, there is a EMF going to be induced. The EMF going to be induced will be there only till there is a change. If there is no change, no EMF. The magnitude of the EMF induced is directly proportional to the rate of change of magnetic flux linked with the coil. So the rate of change of magnetic flux linked with the coil is going to give you the magnitude of the EMF induced in the coil. If magnetic flux changes at a constant rate, the steady EMF is produced. If the circuit is in the coil is closed, the current flows in it due to the EMF induced across the ends. Factors affecting the magnitude of induced EMF. The magnitude of EMF induced in the coil is equal to the product of the rate of change of magnetic flux linked with each turn of the coil and the number of turns in the coil. Hence, induced EMF is change in the magnetic flux of each turn into number of turns in the coil upon time in which the magnetic flux changes. So thus, for a given coil, the magnet it depends on the following two factors. On the rate of change of magnetic flux with each turns. So rate of change of magnetic flux with each turns over here. And secondly, on number of turns in the coil. So number of turns in the coil. Now we move on to the next part, that is the direction of induced EMF. So let's see the direction of the induced EMF. Just say direction of the force which was by the Fleming's left hand rule. Now we'll be having similar one, but it will be Fleming's right hand rule. So the direction of the induced EMF and hence the direction of the induced current depends on whether there is an increase or decrease in the magnetic flux. It can be obtained by any of the following two rules: Fleming's right hand rule and Lenz's law. First is Fleming's right hand rule. Same thing. Stretch the thumb, center finger, the forefinger of your right hand mutually perpendicular to each other as shown. So that was by the left hand, now we are doing with the right hand. If the forefinger indicates the direction of the magnetic field, yeah, same thing, same mother hi, abhi bhi ye mother hi hai, okay. The thumb indicates the direction of the force, direction of the motion of the conductor, yeah, direction of motion of the conductor, usme force tha, but here is the same thing, the direction of motion. Here also the force was giving the direction of the motion. So here also it gives the direction of the motion. And this will give the direction of the current. वो भी current ही था. So it is the same thing. This was father, mother, child. This is also father, mother, child. Father, force, or we can say motion ka direction. Mother, magnetic field. Child is the current. So it is this way. So they are mutually perpendicular to each other. So it is given that then the central finger indicates the direction of the induced current. So this is, note the Fleming's left hand rule gives the direction of the force on a current carrying conductor placed in the magnetic field, but the Fleming's right hand rule gives the direction of the induced current in the conductor moving in the magnetic field. So that is the Fleming's right hand rule. Very important. Remember this thing that left hand is for DC motor, right hand is for AC generator. Left is D, right is AC. The second is Lenz's law. According to the Lenz's law, the direction of induced EMF or induced current is such that it opposes the cause which produces it. So this is important, that Lenz's law states that the direction of the current will always be opposite to the very cause of its existence. Like for example, when we see that particular figure, so ये particular figure में हमने देखा था, this were the coils over here, and I told you that when this particular magnet is such that this is the north pole and this is the south pole, If the north pole is coming near, it is producing a north pole here. And when this is going away, at that time, the north pole is here, then this is producing a south pole here. So the direction is such that it is opposing the very cause of it. Like, see this way. अगर ये नॉर्थ पोल है अगर ये साउथ पोल होता तो it would have automatically attracted each other. But here what is going to happen? It is going to repel each other. ये नॉर्थ है तो ये नॉर्थ बनेगा यानी रिपेल करने के ट्राई करेगा. Whereas अभी उसको अलग जाना है. When it is going away, at that time it is attracting. It is trying to attract because that is the south pole. And this is because we can also say this is also conforming to the law of conservation of energy. Because energy cannot, अगर ये अपने आप पास में आने वाला था, because this was a south pole, then it will come by its own, then it doesn't require a mechanical energy and the electrical energy will be generated, which is not possible. You cannot generate electricity without converting some another energy into this form. So here, it is this way that when you are bringing it closer, it is trying to repel. And when you are going away, it is trying to attract. So this is nothing but Lenz's law. That is, according to Lenz's law, the direction of induced EMF, the direction of the induced EMF or the induced current is such that it opposes the cause. It opposes the cause which produces it. In figure 10.29b, when the north pole of the magnet is brought towards the end A of the solenoid, the induced current flows in the solenoid in direction B to A, and at the end A, the current is clockwise, and so the end A of the solenoid becomes the north pole to repel the magnet. Okay, that's what we say. This point is going to be such that it repels the magnet. Thus, it opposes the motion of the north pole of the magnet towards the solenoid, which is the cause of its producing it. Similarly, in figure 10.29d, the north pole of the magnet recedes from its end A of the solenoid in the direction of the induced current in the solenoid at the end A, and it becomes the south pole so as to oppose the motion of the north pole of the magnet away from the solenoid, which is the cause of producing it. Lenz's law is based on the law of conservation of energy. It shows that the mechanical energy is spent in doing work against the opposing force experienced by the moving magnet, and it is transformed into electrical energy due to which current flows in the solenoid. So that is confirming the law of conservation of energy, that you cannot generate electricity or any energy by itself. You need to convert it. The work has to be done over here so that the electrical energy can be generated. So that is about the Lenz's law. Now we move on to the next part of the chapter, that is AC generator. I'll do it in the next video.